Forward, Introduction, and the Mechanics of Nuclear Explosions in Worldwide Effects of Nuclear War. Some Perspectives. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading by Allyson Hester of Athens, Georgia. Worldwide Effects of Nuclear War. Some Perspectives by U.S. Arms Control and Disarmament Agency in 1975. Forward. Much research has been devoted to the effects of nuclear weapons, but studies have been concerned for the most part with those immediate consequences which would be suffered by a country that was the direct target of nuclear attack. Relatively few studies have examined the worldwide long-term effects. Realistic and responsible arms control policy calls for our knowing more about these wider effects and for making this knowledge available to the public. To learn more about them, the Arms Control and Disarmament Agency, ACDA, has initiated a number of projects, including a National Academy of Sciences study requested in April 1974. The Academy study, Long-Term Worldwide Effects of Multiple Nuclear Weapons Detonations, a highly technical document of more than 200 pages, is now available. The present brief publication seeks to include its essential findings, along with the results of related studies of this agency, and to provide as well the basic background facts necessary for informed perspectives on the issue. New discoveries have been made, yet much uncertainty inevitably persists. Our knowledge of nuclear warfare rests largely on theory and hypothesis, fortunately untested by the usual processes of trial and error. The paramount goal of statesmanship is that we should never learn from the experience of nuclear war. The uncertainties that remain are of such magnitude that, of themselves, they must serve a further deterrent to the use of nuclear weapons. At the same time, knowledge, even fragmentary knowledge, of the broader effects of nuclear weapons underlines the extreme difficulty that strategic planners of any nation would face in attempting to predict the results of a nuclear war. Uncertainty is one of the major conclusions in our studies, as the haphazard and unpredicted derivation of many of our discoveries emphasizes. Moreover, it now appears that a massive attack with many large-scale nuclear detonations could cause such widespread and long-lasting environmental damage that the aggressor country might suffer serious physiological, economic, and environmental effects even without a nuclear response by the country attacked. An effort has been made to present this paper in language that does not require a scientific background on the part of the reader. Nevertheless, it must deal in schematized processes, abstractions, and statistical generalizations. Hence, one supremely important perspective must be largely supplied by the reader: the human perspective, the meaning of these physical effects for individual human beings and for the fabric of civilized life. Forward by Fred C. Eichel, Director of U.S. Arms Control and Disarmament Agency. Introduction. It has now been 2 decades since the introduction of thermonuclear fusion weapons into the military inventories of the great powers, and more than a decade since the United States, Great Britain, and the Soviet Union ceased to test nuclear weapons in the atmosphere. Today, our understanding of the technology of thermonuclear weapons seems highly advanced, but our knowledge of the physical and biological consequences of nuclear war is continuously evolving. Only recently, new light was shed on the subject in a study which the Arms Control and Disarmament Agency had asked the National Academy of Sciences to undertake. Previous studies had tended to focus very largely on radioactive fallout from a nuclear war. An important aspect of this new study was its inquiry into all possible consequences, including the effects of large-scale nuclear detonations on the ozone layer, which helps protect life on Earth from the sun's ultraviolet radiations. Assuming a total detonation of 10,000 megatons, a large-scale but less than total nuclear exchange, as one would say in the dehumanizing jargon of the strategists, it was concluded that as much as 30 to 70% of the ozone might be eliminated from the northern hemisphere, where a nuclear war would presumably take place, and as much as 20 to 40% from the southern hemisphere. Recovery would probably take about 3 to 10 years, but the Academy's study notes that long-term global changes cannot be completely ruled out. The reduced ozone concentrations would have a number of consequences outside the areas in which the detonations occurred. The Academy study notes, for example, that the resultant increase in ultraviolet would cause, quote, prompt incapacitating cases of sunburn in the temperate zones and snow blindness in the northern countries, end quote. Strange though it might seem, the increased ultraviolet radiation could also be accompanied by a drop in the average temperature. The size of the change is open to question, but the largest changes would probably occur at the higher latitudes, where crop production and ecological balances are sensitively dependent upon the number of frost-free days and other factors related to average temperature. The Academy's study concluded that ozone changes due to nuclear war might decrease global surface temperatures by only negligible amounts or by as much as a few degrees. To calibrate the significance of this, the study mentioned that a cooling of even 1 degree centigrade would eliminate commercial wheat growing in Canada. Thus, the possibility of a serious increase in ultraviolet radiation has been added to widespread radioactive fallout as a fearsome consequence of the large-scale use of nuclear weapons. And it is likely that we must reckon with still other complex and subtle processes, global in scope, which could seriously threaten the health of distant populations in the event of an all-out nuclear war. Up to now, many of the important discoveries about nuclear weapon effects have been made not through deliberate scientific inquiry, but by accident. And as the following historical examples show, there has been a series of surprises. Castle Bravo was the largest nuclear weapon ever detonated by the United States. Before it was set off at Bikini on February 28, 1954, it was expected to explode with an energy equivalent of about 8 million tons of TNT. Actually, it produced almost twice that explosive power, equivalent to 15 million tons of TNT. If the power of the bomb was unexpected, so were the after effects. About 6 hours after the explosion, a fine, sandy ash began to sprinkle the Japanese fishing vessel Lucky Dragon, some 90 miles downwind of the burst point, and Rongelap Atoll, 100 miles downwind. Though 40 to 50 miles away from the prescribed test area, the vessel's crew and the islanders received heavy doses of radiation from the weapon's fallout. The coral rock, soil, and other debris sucked up in the fireball and made intensively radioactive by the nuclear reaction. One radioactive isotope in the fallout, iodine-131, rapidly built up to serious concentration in the thyroid glands of the victims, particularly young Rongelapese children. More than any other event in the decade of testing large nuclear weapons in the atmosphere, Castle Bravo's unexpected contamination of 7,000 square miles of the Pacific Ocean dramatically illustrated how large-scale nuclear war could produce casualties on a colossal scale, far beyond the local effects of blast and fire alone. A number of other surprises were encountered during 30 years of nuclear weapons development. For example, What was probably man's most extensive modification of the global environment to date occurred in September 1962 when a nuclear device was detonated 250 miles above Johnson Island. The 1.4 megaton burst produced an artificial belt of charged particles trapped in the Earth's magnetic field. Though 98% of these particles were removed by natural processes after the first year, traces could be detected 6 or 7 years later. A number of satellites in low Earth orbit at the time of the burst suffered severe electronic damage, resulting in malfunctions and early failure. It became obvious that man now had the power to make long-term changes in his near-space environment. Another unexpected effect of high-altitude bursts was the blackout of high-frequency radio communications. Disruption of the ionosphere, which reflects radio signals back to the Earth, by nuclear bursts over the Pacific has wiped out long-distance radio communications for hours at distances of up to 600 miles from the burst point. Yet another surprise was the discovery that electromagnetic pulses can play havoc with electrical equipment itself, including some in command systems that control the nuclear arms themselves. Much of our knowledge was thus gained by chance, a fact which should imbue us with humility as we contemplate the remaining uncertainties, as well as the certainties, about nuclear warfare. What we have learned enables us, nonetheless, to see more clearly. We know, for instance, that some of the earlier speculations about the after effects of a global nuclear war were as far-fetched as they were horrifying, such as the idea that the worldwide accumulation of radioactive fallout would eliminate all life on the planet, or that it might produce a train of monstrous genetic mutations in all living things, making future life unrecognizable. And this accumulation of knowledge, which enables us to rule out the more fanciful possibilities, also allows us to re-examine, with some scientific rigor, other phenomena which could seriously affect the global environment and the populations of participant and non-participant countries alike. This paper is an attempt to set in perspective some of the longer-term effects of nuclear war on the global environment, with emphasis on areas and people distant from the actual targets of the weapons. End of introduction. The mechanics of nuclear explosions. In nuclear explosions, about 90% of the energy is released in less than 1/millionth of a second. Most of this is in the form of the heat and shock waves which produce the damage. It is this immediate and direct explosive power which could devastate the urban centers in a major nuclear war. Compared with the immediate colossal destruction suffered in target areas, the more subtle, longer-term effects of the remaining 10% of the energy released by nuclear weapons might seem a matter of secondary concern, but the dimensions of the initial catastrophe should not overshadow the after-effects of a nuclear war. They would be global, affecting nations remote from the fighting for many years after the Holocaust, because of the way nuclear explosions behave in the atmosphere and the radioactive products released by nuclear bursts. When a weapon is detonated at the surface of the Earth, or at low altitudes, the heat pulse vaporizes the bomb material, target, nearby structures, and underlying soil and rock, all of which become entrained in an expanding, fast-rising fireball. As the fireball rises, it expands and cools, producing the distinctive mushroom cloud, signature of nuclear explosions. The altitude reached by the cloud depends on the force of the explosion. When yields are in the low kiloton range, the cloud will remain in the lower atmosphere and its effects will be entirely local. But as yields exceed 30 kilotons, part of the cloud will punch into the stratosphere, which begins about 7 miles up. With yields of 2 to 5 megatons or more, virtually all of the cloud of radioactive debris and fine dust will climb into the stratosphere. The heavier materials reaching the lower edge of the stratosphere will soon settle out, as did the Castle Bravo fallout at Rongelap. But the lighter particles will penetrate high into the stratosphere, to altitudes of 12 miles or more, and remain there for months and even years. Stratospheric circulation and diffusion will spread this material around the world. End of the mechanics of nuclear explosion. End of Part 1 of Worldwide Effects of Nuclear War.